Today we're going to talk about congruent and similar solids. So we're talking about three-dimensional figures. We're going to look at properties of three-dimensional figures, whether it be dimensions of them, surface areas, or volumes, okay, and how they're all related to each other and how we can use proportions to help us solve for, say, surface area when we know volume without having to actually calculate surface area. Okay, so that's what our focus is for today. So we talked about similar triangles, similar figures. Well, we can also have similar three-dimensional shapes. So for instance, here we have two cones. I want to know, are they similar? Okay, are the cones similar? So I just need to compare corresponding parts, like the heights. So I would compare 15 to 12. I can compare the radii, 8 to 5. And I can compare the slant heights, 17 to 13. So when I type those into my calculator, I just need to see, do I have the same ratio each and every time? So if I take 15 divided by 12, 15 twelfths is 1.25, 8 fifths is 1.6. Okay, I really don't even have to go any further because I already have conflicting ratios, so it's already done. But these are not the same, not all the exact same ratio, therefore they are not similar. Okay, so that shouldn't really be anything different other than we can test all the dimensions of it. All right, so here's where I think it gets interesting. There's similarity ratio between one-dimensional objects, two-dimensional objects, and three-dimensional objects. So I want to talk about, first of all, things that are one-dimensional. So measurements that are going to be one-dimensional are going to be like length, width, perimeter. Okay, we're talking about circumference. We're talking about things that can be measured with a ruler. Okay, things in the one dimension can be measured with a ruler. Okay, when you're talking about area, okay, area is two-dimensional. So usually you're talking about surface area. Oops. You could talk about the area of a base or lateral area, anything literally with the word area in it. Three-dimensional measurements are going to be volume, and weight is actually three-dimensional as well. Okay, so everything that we talk about with three-dimensional objects is either going to fall into the one-dimensional category, two-dimensional, or three-dimensional. And they're really kind of like their own language, and what we have to do is translate from one language to the other. Okay, so the relationship between these is whatever the one-dimensional ratio is, let's say A to B, okay, the area is going to be A squared to B squared. Volume is going to be A cubed to B cubed. So sometimes what happens is we're given information in terms of volume, which is a three-dimensional measurement, and we have to go back to the one-dimensional measurement. Okay, so an example is, let's say we have two figures whose volumes are in a ratio of 8 to 27. Okay, so 8 to 27, since it's volume, I'm going to put it under the 3D category. Okay, so I want to know the ratios of their surface areas. So I want to know two-dimensionally. So what I want to do first is I want to take it back to 1D. If I want to go back to the first dimension, in order to go from A cubed back to A, I would need to take the cube root. So the cube root of 8 is going to be 2. The cube root of 27 is 3. So any figure, these figures that are the volumes in a ratio of 8 to 27, their dimensions, whether it be a cube or like a cone, whatever it may be, their dimensions are in a ratio of 2 to 3. Their areas are going to be in a ratio of 2 squared to 3 squared, or 4 to 9. Okay, so that's the first thing we need to understand. So let's just take a look at an example like that, and then I'm going to show you how it really applies. All right, so disco balls are spheres that are covered with reflexive tiles. One ball has a diameter of 4 inches, another has a diameter of 20 inches. Okay, so my scale factor is just comparing the 4 to the 20. Okay, so that is my one-dimensional measurement. And I'm actually going to go ahead and reduce this just to make our lives a little easier and work with smaller numbers. Okay, so 4 to 20 reduces down to 1 to 5. Okay, diameter, remember, that could be measured with a ruler. That is just one-dimensional. I want to know now what's the ratio if we are looking at surface area. So that is two-dimensional. So I need to square my ratio. So 1 squared to 5 squared, or 1 to 25. So the surface area of the larger figure is 25 times that of the smaller one in our case. Then finally we have, I want to compare the volume. Okay, volume is three-dimensional. So I'm going to take my original 1 to 5 and I need to cube those. So the volumes are going to be in a ratio of 1 to 125. Okay, so that is just looking at the ratios and how they compare. Okay, here's how it's actually applied. It says the lateral area of two smaller cylinders are 196 pi and 324 pi. The volume of the smaller cylinder is 686 pi cubic inches. Find the volume of the larger cylinder. All right, so first of all, we're given lateral area. Okay, so lateral area, I know that is 2D. Okay, so we have two similar cylinders, two-dimensionally. I'm going to think about 2D here. They're in a ratio of 196 to 324 pi on both of those. Okay, so first of all, I want to try to simplify that by, I'm just going to divide out a pi. I first need to go back to one dimension. So to go from 2D to 1D, keep in mind this was a squared to b squared. I want to go back to a to b. So I need to take the square root of each of those. So that's going to give me, the square root of 196 is 14. And then the square root of 324 is 18. Okay, now that's not reduced, so I'm going to reduce it just because I don't want to work with larger numbers and I have to. That would be the equivalent to 7/9. Okay, now I want to find volume, right? I'm trying to find volume, and I know volume is in 3D. So I need to take this ratio to 3D. So I'm talking 7 cubed to 9 cubed. So 7 cubed, I believe, is 343. Yes, 343 to 9 cubed is 729. This becomes one of my fractions in my proportion. So the smaller one would obviously be 343. The larger is going to be 729. Okay, now we're given that the volume of the smaller cylinder, right here, the volume of the smaller cylinder is 686 pi. So again, the smaller was on top, the larger was on the bottom here. Okay, so up here in my numerator, I'm going to have 686 pi over, I'm trying to find the volume of the larger cylinder. And this is a proportion I want to solve. So I'm going to go ahead and cross multiply. I'm going to move over here because I have more room. So I have 343x equals 729 times 686 gives me 500,094 pi. Divide both sides by 343. So x is equal to 1,458 pi. Well, let's see, what are we in? Cubic inches. Okay, so that may have seemed like a lot, but keep in mind, I don't really know anything about the dimension of those cylinders other than I know what their surface areas are. And just knowing that grand total, I know then I can take it back to a one-dimensional ratio, then convert it to a three-dimensional ratio, and I'm able to then know one volume and find the other volume. Okay, so we just found volume without knowing, in our case, cylinders. So we didn't know the radius, we didn't know the height, we didn't know any of that. But we didn't actually have to go through that calculation. We just saw how they're all related. This is what you're going to be practicing both today and tomorrow. Okay, this is not the easiest thing to get, but once you understand what you're doing, it seems to go much faster. Okay, so your homework for tonight is on page 595 through 598, numbers 1 through 8 and 10 through 16. Go ahead and work on that now.